Hi, welcome back to Kirsty's virtual classroom. Today in California Geology, we are talking about the Transverse Ranges. So the Transverse Ranges is down just before you hit the LA basin. So it is actually an east-west trending set of mountain ranges that we're going to talk about why they do not trend the north-south as with most of the other mountain ranges in California. So here's a look at what they look like if you've never transversed the transverse ranges. You will go through these mountains when you go down I-5. So here's just kind of a look, LA Basin being down here at the bottom right and Bakersfield up here at the top left. Okay, so although we refer to these as ranges in a collective group, they have very a significant amount of mountain ranges compared to a lot of the other ranges we'll talk about. So within this province, we see the Santa Ynez and the Topa Topa Mountains, the Oak Ridge and the Santa Susana Mountains, Santa Clara and Semi Valleys, Santa Monica Mountains, San Gabriel Mountains, San Bernardino Mountains, Little San Bernardino Mountains, Pinto Mountains, and Eagle and Cottonwood Mountains. So quite a few different mountain ranges. So the plate tectonic history, just briefly, in the Mesozoic, we saw a lot of subduction and accretion. So we've talked a lot about that already with Klamath this week. And then in the mid-Cenozoic, we saw extension and rotation. And then in the Cenozoic, we saw transform motion and transpression. And we're going to focus on that a little bit. The LA Basin and the San Andreas Fault are at odds basically every day. Right now we know that the LA Basin is keeping it locked and there's not a lot of movement along the San Andreas Fault in that area. And that is largely because of the type of rock that we see in the LA Basin and the Transverse Ranges. The rock there is much stiffer. It doesn't allow for a lot of slip to occur. Whereas when you move north along the San Andreas Fault, there's a lot more serpentinite. And serpentinite is very slippery and it allows for a lot of slip along the fault, which is good in those areas because they can get very frequent small earthquakes. But in areas where we have a lot of interlocking rocks like the Transverse Ranges in the LA Basin, we're going to see a lot less frequent earthquakes, which is going to build up a lot of stress and cause a very large earthquake in the future. So the mountains and basins here are separated by reverse faults and the strike-slip fault of the San Andreas Fault system. The Los Angeles Basin and the Transverse Ranges are crisscrossed by reverse faults and folds. We'll talk about folds in a second. The faults and folds tend to trend east-west, and they intersect the north-south trending right lateral San Andreas Fault system. So here's kind of a look at that. This is the San Andreas Fault here that's doing most of the movement in California. And then we also see the Garlock Fault, which is a left lateral strike-slip fault here. And then there are a number of reverse faults, which is what all of these lines with little triangles on them are. Those are some of our reverse or thrust faults. You'll see them referred to as. And they are thrust faults when they are much shallower. So it's got a shallower angle on the fault. So like this fault here, this fault is more of a, traditional fault, but if it was a little bit angled up, the angle is at a lower angle to basically the surface. We call those thrust faults, but they're still the same type of movement. They're still a reverse hanging wall up reverse, if you remember. Let's talk about the Ventura Basin. This is sandwiched between the Santa Ynez and the Santa Monica Mountains. The ranges are moving toward each other, squeezing the basin and deforming the sediments in it. So we see some slight metamorphism of the sediments in the Ventura Basin. And it contains the world's thickest section of Pleistocene marine deposits, which is pretty incredible at 10,000 meters of just straight Pleistocene marine deposits. In the early Cenozoic and Mesozoic, we saw rocks that were greatly deformed by faulting and folding. They came from the marine basin, basically, that existed before California existed. We talked about that with Klamath Mountains. And they match some of the Great Valley sequence. So they seem to be similar rocks, but they have been severely deformed. They may have formed simultaneously in the Forearc Basin between the San Andreas developed. During the early Oligocene, uplift brought these rocks above the sea level, and then marine conditions returned during Miocene time and remained until the Pliocene. The Miocene extension and rotation is basically why we see the ranges not aligned with the rest of the ranges in California. So Miocene deposits are lacking marine rocks, and multiple volcanoes are happening during this time. And this is when the transverse ranges start to rotate 90 degrees clockwise during the Miocene, and then paleomagnetism of these rocks assist in this conclusion. So we talked a little bit about paleomagnetism with plate tectonics. So remember, paleomagnetism is looking at magnetic minerals and rocks and their orientation. And so when they are first deposited, they orient themselves to magnetic north, right? And if those rocks are rotated in any fashion, like in this rotation of these ranges, it will indicate that in their paleomagnetic record. And we can see that in lab samples, basically. So we take samples from the rocks and then we bring them back to the lab, demagnetize them, and then look at their rotation. Some of the basins were formed via extension, like the Santa Maria Basin and Los Angeles Basin. So looking at what this rotation would look like, in the Cenozoic, we saw the formation of the San Andreas Fault, which started the rotation of the transverse ranges. This opened up the basins, which are between these ranges. So here's the rocks that existed prior to any rotation and the deformation of the San Andreas Fault. These ranges lie between the San Andreas Fault as it moves, and as the eastern portion of the San Andreas Fault moves south east, and the western portion moves northwest, it starts to drag those ranges and rotates them. And so they were at a different orientation than they are today. But the San Andreas Fault, them being smack dab in the middle of it, has rotated them and has opened up all of these basins, which are what all these gray areas are. So the transverse block has rotated approximately 80 to 110 degrees from its original orientation. This rotation occurred during the evolution of the current plate boundary, which is the transformed plate boundary that we see along the San Andreas Fault that separates the North American plate and the Pacific plate. This took place in 3 stages, though. We had subduction first of the Farallon plate, transtension, and transpression. In the Mesozoic, the western edge of North America was a subduction zone with the Farallon plate subducting eastwards underneath North America. We talked about that several times so far, just kind of reiterating every time we go through one of these provinces. So in the Santa Ynez, Tapatoa, and Santa Monica Mountains, we have very large anticlines. And if you remember from the Faults and Folds lecture, anticlines are concave down. So you can fit like a big A in them, which is what I had you guys remember. And anticlines are important in California because this is what traps oil and gas. And so we can then find these anticlines and use them for oil production. So here's a look at the San Gabriel Mountains. Looking east, we have the Santa Susana Mountains. We have the Santa Clara River, Here's the San Gabriel Mountains, which are some of the highest peaks, and then Antelope Valley out in the distance there. Mount San Antonio is the highest point in the Transverse Ranges at an elevation of 10,066 feet. So here's a cross-section of Mount San Antonio. This is really interesting because we can see some underlying schist, and then we see lots of these thrust systems. So remember, these thrust faults are reverse faults. They are just at a smaller angle. So the angle that we see movement is shallow. Um, there's a lot of other faults that are listed here, like Pinch Bowl Fault, Icehouse Canyon Fault, San Andrew Fault. So there's a lot of fault motion in the area. A lot of them are relative to the San Andreas Fault system. But these stress faults are what cause a lot of the excess movement outside of the San Andreas Fault system in here. So the Vincent thrust in the San Gabriel Mountains is capable of producing a lot of really, really deformed rocks. So we see lower plate rocks that are complex metamorphosed sedimentary and volcanic rocks. We call these the Pelanosis schist, which is a rock unit whose pre-metamorphic protolith consisted of Mesozoic, perhaps Jurassic and Cretaceous, marine deepwater sand, silt, calcareous, and siliceous mud located locally interlaid, with basaltic flows. So the basaltic flows being the volcanic component of that, and then all of those other sand, silt, calcareous, and siliceous mud being the sedimentary component of that, and all of which are metamorphosed into this schist that I pointed to here. So this is the Vincent thrust here that we're talking about. Okay, so then the upper plate rocks are crystalline rock that is complex that directly overlays the Vincent thrust, consists of mainly gneissic layered metamorphic rock. So remember, gneissic material or gneiss rocks are basically black and white banded rocks that were previously granitic. So remember, they were granites before, now they are gneiss from the metamorphism. We also see associated metasedimentary rocks that have been complexly deformed under deep-seated ductile metamorphic conditions that locally yield myelinite at the end product. So remember, ductile deformation is the bending of rocks. Okay, so we're not breaking, there's no faulting happening there. So the rocks that we see near the Vincent thrust are highly metamorphosed. So here's a look at that schist. You can see some of the bending in here. Some of the mica minerals are in here. And then we have the non-micaceous material there. Here's a look at the myelinite, which is basically a highly metamorphosed rock that has gone through very intense shearing. So remember, shearing is the side-to-side motion. It's the same motion that we see in a strike slip fault or a transform plate boundary. And these rocks have experienced significant shearing along the Vincent thrust. Then we see the gneiss. So here's the black and white banding. It's very indicative from the mafic to felsic mineral differences here. So we see some quartz and some plagioclase in here, and then probably some hornblendes and biotites. And then we see some myelinitic cataclastic rocks in the San Bernardino Mountains. These are, they previously were clastic sedimentary rocks that have been severely deformed by the fault and the shearing along the fault. So let's look at the Miocene Monterey Formation. So this deposited between 12 and 23 million years ago. It's exposed throughout coastal California, so it's not just present in the Transverse Ranges, but it's present in other provinces as well. The source rock for most of California's petroleum. So remember, I was talking about petroleum being trapped in anticlines. This is where we're going to see a lot of that petroleum. It's composed of mostly deep water sediments with little to no terrestrial input. So most of this material came from that oceanic plate. We see siliceous sediment mostly in the form of diatomite. And it also contains porcelainite and dolomite. Here is a look at the diatoms in an electron micrograph. So this is very, very small. So this is kind of what they look like. They are porous. Here's another look at the diatoms and some of the different shapes that you would see them in. So this is what's helping to produce the petroleum. Here's a look at a field photo of what the Monterey Formation would look like. Here are some of the rocks that are not necessarily the petroleum product, and it's a lot of the dolomite that is kind of a lighter color. The porcelainite looks a little bit like this, and it's mostly a very, very impure variety of chert. So if you remember, chert is a precipitate mineral. It's a biochemical, or not mineral, rock. It's a biochemical sedimentary rock that forms primarily from precipitation of minerals. So here's a look at what the Monterey Formation oil would look like. You can kind of see some of the different banding in here. The black ooze that you might see in these rocks is the petroleum seeping out of the rock. So in the Los Angeles Basin in particular, there are a lot of oil fields. So all of these yellow areas are oil fields. So you'll see quite a few oil pumps in these areas because that's where we can get a lot of production in California anyway. Here's a look at the Ventura Basin, which is where we get a lot of that oil. So the Ventura Basin cross-section here shows you the anticline. So here's the concave down formation of these rocks. So all of these lines separate the different rock types. And this one here shows the anticline. Here's the Monterey Formation. Here's a fault that's also helping thrust that material upwards, and we can actually extract petroleum out of this anticline. Here is the Brea Olinda oil fields. Have you ever heard of the La Brea tar pits? This is related. The tar is coming from one of these anticlines. So here's a look at this anticline here, and we also see the Whittier fault here that is thrusting this material upwards and allowing us to actually tap into it much more easily. So petroleum was first discovered in California in 1769, and it was used to seal canoes by Indians primarily. And they named the first site Carpinteria. And later in the 1890s, Edward Doheny noticed people would use the Brea to seal their roofs. So he partnered with Charles Canfield, leased a lot, dug a hole, and struck oil, starting the first oil boom. So this has been a long time coming with oil. So by 1900, more than 1,000 oil companies were drilling in California. The peak production in the 1920s was at 850,000 barrels per day. Most of this was happening in Long Beach and the Huntington Beach areas. July 2012, California produced 530,000 barrels per day, and in 2018, 463,000 barrels per day. So you can see that California is losing its oil. We are diminishing our oil production in California significantly, and that is why we have turned to a lot of the other oil-bearing countries like Iraq and Saudi Arabia, who can produce up to 3 million or 10 million barrels per day, which is significantly more than we've ever produced in California. So how does this process work? So what first happens is the material is extracted, the petroleum is extracted from the earth, and then it is put into this boiler. And this boiler superheats the material and causes it to form into a vapor. So all of the material forms into a vapor and then is pushed into this distillation column or distillation chamber. And in this chamber, the material starts to cool. It rises because it's been heated, and it starts to cool, and it separates out by density. And then most of these systems have trays that separate the liquids, and the densest stuff, the stuff that is the heaviest, ends up taking the longest to process. So that would be like your heavy gas oil, your residual And then gas is the quickest to produce and process. It has far less carbons, which is why the processing is a lot quicker. The higher the carbon count, the heavier the material is, and the longer it takes to produce it before we can actually use it for something. So obviously gas can be used for things like propane. We can use it in cars, and then we've got jet fuel, diesel fuel, kind of in the in between, and then any fuels for ships or any petroleum that we use for roofing or roads takes the longest to actually process and then be useful. The oldest rocks in the Transverse Ranges are plutonic rocks that are below the San Gabriel Mountains. Those are 1.3 billion years old. And then we see the Mendenhall, nice, in San Gabriel Mountains, 1.6 billion years old. And both of those are involved in the Vincent thrust. So they were placed Precambrian basement on top of the Mesozoic basement rocks. Here's a look at that gneiss. Again, we see some black and white banding. This one actually has a few different garnets in it. And it does look, this one actually looks pretty weathered. So again, the transverse ranges, are basically between the LA Basin and the Great Valley sequence. And they have numerous thrust faults in the area, and they are sandwiched between the San Andreas fault system. All right, that's it for the transverse ranges. I will catch you guys in the next video. Bye.